the same thing. Yeah. But you need to put, right here, change that to 1 over pressure. Or is it pressure of gas?
The formula's right.
Oh, the formula's perfect. Yeah, but right here, this x-axis should be, just put a dash of 1 over the pressure of gas. And that's 3. Okay, so that was it. Big mistake. Okay. I wanna work a few more problems. Before we do the stoichiometry all right, we're going to do a problem. And I'm going to make up on the fly. Let's save somebody's life. So that is a oxygen tank, metal cylinder, 50 liters, oxygen. Right now, the pressure inside this tank is making up a number here, 81.654 atmosphere. 81.654 atmosphere. That's 81.654. That is the pressure inside that container, that 50-liter container. Is that clear? Who's this? That's not here.
Dash.
Okay. Okay. What's her name?
I don't know why you said it.
He doesn't know your name.
No, I know her name, Lexi.
Oh, but he doesn't know your name.
Who is that?
Lexi.
Yeah.
Can I pick you?
You say that.
Okay, this is Lexi. This will be fun. We haven't had a girl all. Okay, there's Lexi. Okay, now, Lexi, we're going to save your life. Lexi was rock climbing one day, and she fell off. Lexi, not very happy. Now, what happened? She fell on a rock. This is a good one. I got a plan. She fell on a rock and totally collapsed her lungs. So right now she is dying. Okay, because she has no oxygen. Her lungs aren't working. They're completely flat. They're collapsed. Now, does anybody know, and we can actually do this experiment in the lab if you want to, you can do it at home. But do you know what your lung capacity is in volume in liters? Like, if you were to fill your lungs up fully with oxygen or air, how much could you hold? That's pretty close. It's about 2.5, 3 liters, yeah. So, but we're going to say it's exactly 3 liters. We're going to say 3 liters of air. So her lungs, so she has a 3.0 liter lung capacity. Is that clear? Now, here's what we got to do for her. We have got to inflate her lungs back up to 3 liters. Now, one thing dangerous could happen, because what we're going to use is this pressurized oxygen tank. And we're going to basically take and put a mask over her mouth and her nose, and we're going to force air into her lungs. And we're going to expand her lungs back to 3.0 liters. If we go any larger than 3.0 liters, what happens to Lexi? Lexi. She dies. Okay, now, if we do not get it to 3 liters, so I'm going to make it a little critical that we get exactly right. If we don't get it exactly to 3 liters, so 2.7 liters, we take the mask off, it deflates again. It's going to be good. We got to get it to 3 liters. Her lungs have to be filled up to 3 liters. Is that clear? Yes. Now, outside in this area, the temperature on the wall says it is 28 all we need. Now, I want you to help me savor. How are we going to do this experiment? Lindsay's got about 5 minutes before she starts having brain issues. So we have got to get those lungs filled up in 5 minutes and do it safely. This is the equipment you've got. Tell me how you're going to solve this problem. Save our life. Tell me what you're going to do. Physically tell me how you're going to do it. Verbally tell me. So this is what I'm going to do. I'm going to do this, do that, and this is exactly going to happen.
Put 3 liters in.
Now, how are you going to do that?
You just open the nozzle.
And how her lungs flow up? There's not a mark on it that says ding, 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 going into her lungs. None of them is variables. You can do it. You've got information up. What happens? Let me ask you this. What's going to happen to the pressure in that tank if I start releasing some of the oxygen? It's going to go down. Okay, so there you've got a way of measuring. It's not going to say 3 liters. You know, because that's, remember, that's under a pressurized, that's 84 atmosphere, or 81.654 atmospheres of pressure. Yes, who was going to say something? Yeah. Okay, she's got a plan. She said, well, we got to figure out how much of that gas that we're going to let out of that container that's going to actually be exactly the correct number of moles, if you will, that will fill up Lindsay's 3-liter lungs, or lexicon. What's your name? Lexi. We got to fill up her lungs completely. So that's exactly how we're going to do it. Now, look, here, I'm going to give you an idea. This is what you got to be doing here. You're going to put the mask on Lindsay. You're going to open up the valve. What's going to happen is the pressure in the valve is going to go down. So it's going to come down to another number. You need to know what is that number. What is that final pressure? If you know that final pressure, and then you turn it on, clink, 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 stop. Right at that pressure, then you know, okay, you put enough pressure or air in her lungs to satisfy 3 liters at that temperature and pressure. So now I told you how to do it, so save her life. There's a couple ways you can do this, but just do your best. We're pulling for you, Lexi. right, who's got an answer? Who's gonna say Lexi? Lexi. I got one guy back here. No, you're not a saver. You got an answer that's not good. Might be right. Anybody else? Come on, this is practical stuff here. This guy's got an answer. He's gonna be the only guy that's gonna save you. What you got, sir? Tell me your answer. 86. See, that would mean that the pressure actually went up. Oh, you are trying to compress the. He's trying to compress that metal cylinder. Can't do that. I see what you're thinking. No. Somebody else. The metal cylinder, you can't compress that to try. I see what you're doing though. Can you tell me this? How many moles of gas do you need to fill up her lungs? That's correct. Now that's right. But now you got to figure out a way to get it out of there. Okay, so anybody else? Anybody else? Come on. This is good stuff here. What do you guys, sir? Anybody?
76.75.
76.75 atmospheres? Yeah, that would probably blow her up. Okay? You could probably turn her into a helium-filled balloon. That's not great.
That's how much is left.
Oh, that's the pressure left in. That's what I mean. That's the pressure left in the tank. That's way too much. You let way too much out. Yeah. All right. Anybody? See, look, this is the kind of stuff I like you to learn because this is actually practical stuff. Let's think about it. Okay. Let me walk you through the method, and let's see if you can figure this out. One thing we know for sure, that Lindsay has a lung capacity. Her volume of her lungs is 3 liters. You agree, yes or no?
Yes.
Okay. We also know what the atmospheric pressure is surrounding her lungs. We do know right now you are at equilibrium with the external pressure. Right now, if it's 1.05 atmospheres outside here, inside your body, you are at 1.05 atmospheres. Your lungs right now are under a pressure of 1.05 atmospheres if you're in that cartoon. Is that clear? I know the temperature. Can anybody, hopefully you've done this, have you calculated the number of moles of oxygen I need to put inside of those lungs to get them to exactly 3 liters? Have you figured that out yet? That's pretty straightforward. All you had to do is this, and I kind of wrote it over here. The N is a number of moles, this is for Lexi, is equal to PV over RT. There's the pressure, 1.05 atmospheres, times the volume of the lungs, 3, divided by 0.082, divided by the temperature, 301 Kelvin. That's PV over RT. That is 0.127 moles. So, it's 0.127. Say again. The temperature is 301 because it's 28 degrees Celsius. So it's 1.05 for the atmospheres, 3 liters, 0.081, close enough, for the R constant, and then 301 Kelvin for the temperature. That gave me 0.127 moles. So, I know now, to save her life, we need to put 0.127 moles of oxygen into her lungs, and in all those other variables, the temperature, the pressure, her lungs will get to exactly 3 liters. That makes perfect sense, correct? I hope it does. So now, we just got to figure out, well, how do we get exactly 0.127 moles of gas out of this container? Well, why don't we do this? So before I tell you, why don't you see if you can think of it? How can we do this? Anybody? No? Okay. What is that pressure gauge telling us right now? It's telling us the pressure inside that container. Isn't that directly related to the number of moles of gas inside that container? So that pressure is a direct relationship to the number of moles in the container. So I can go from the number of moles straight to pressure. That's easy. PV equals nRT. We can do that. So if that particular pressure represents some number of moles, when I let out 0.127 moles, isn't that pressure going to go down? So about what is that pressure going to be when that happens? So let me show you. Tell me if this makes sense. So what I did first is I calculated the number of moles of oxygen inside the container. Inside that container to start with. That was simply PV over RT. Pressure, 81.654 atmospheres, that was given. Times the volume of the container is 50 liters. Divided by 0.082, which is gas constant. Times the temperature, which is 301 Kelvin still. That means inside that container is 165.41 moles. That's how many moles of oxygen is inside that container. Is that clear? Okay, now, I'm going to let out exactly 165.412. That's how many moles are in there. I'm going to subtract out 0.127 moles. That's going to leave me in the tank 165.284 moles remaining. If I let out exactly 0.127 moles, I'm going to have in there 165.284 remaining. Is that clear? Yes. Well, what does that correspond to as a pressure? Well, pressure is equal to number of moles, 165.284, times R, 0.082, times temperature, 301, divided by the volume of the container, 50, because it's a still container, it doesn't change. That gives me 81.591 atmosphere. So, there you go. So now I know that if I open up that valve until the pressure drops down to 81.591 atmospheres, I have let out exactly 0.127 moles of gas. Hopefully it went straight into Lexi's lungs and filled her up to exactly 3 liters, and now she lives. Is this great? Don't you love these people? Yes, ma'am.
Okay, so basically we just have to find the moles of that what we needed, and then the moles that was actually in the tank, and subtract those two to find out what was left. And
Pretty
then
much, yeah.
substitute that and find the pressure.
Yeah, I'm trying to think of a good analogy, but like that pressure that I gave you up there, pressure is a direct indicator of number of moles, direct indicator of volume, because you can use PV equals nRT. You know all the other variables are constant, like the volume was constant, the temperature was constant. The pressure is going to change when you let the number of moles out. So pressure is a direct indicator of number of moles. So once you know the number of moles that are in them, and that corresponds to that pressure, when you let out a certain number, whatever number you need. Okay, I think you got this. Well, let's try another one. I want everybody to use the same problem here for a second. Yeah.
Is there an easy way to convert from Celsius to Kelvin?
Just add 273. The 273 is what you add. And don't worry about the 0.15. You should, but it's 273 plus Celsius is Kelvin. 1 second. Everybody do this one. I want everybody to get this right. I'm going to call on you. Let's say that I want to fill a balloon up. A balloon that is 78 liters big. Starting right now with this same container that we were using a while ago, this one. So instead of giving the oxygen to Lindsay, we're going to fill up a balloon. That'll be more fun. So here's a big balloon. The balloon is I want it to be 78.6 liters. So I want you to fill this balloon up. Now tell me what the pressure is going to be inside when you completely fill that balloon up. At 1.05 atmospheres, everything's else the same. What is the pressure in the container? No, we did not give Lindsay any oxygen. We're starting at 81.654. She can wait. Right, the balloon's going to fill up to 78.6 liters. Trust me. Look at the pressure inside here. This is 50 liters. That's only 1.0. I mean, the pressure is 81.654 atmospheres. There's enough in there to fill that balloon up 1,000 times. Just trust me. Do it. Fill this balloon up to 78.6 liters. The pressure is going to be 1.05 atmospheres. The temperature is 28 degrees Celsius. Tell me what the pressure in the container is going to be once you fill that balloon up. I think there's a homework problem like this that deals with meteorological balloons, and you're doing something similar. 1.05 atmospheres. The balloon just expands just like purple. brain works, man. I can do that kind of high level calculation. Just if I know. I was called brain man when I was in high school. I don't know why. Who's got an answer? Everybody better have an answer. As a matter of fact, let me just pick you. What's your name? Yeah, the one that wants to go to town. Natalie, what did you get for that pressure?
80.00.
Yeah, 80.00. Excellent. So the pressure will come down from 81.64. See, young lady? We can fill this balloon up to 78.6 liters. Even though you said, well, it's only a 50-liter container. But there's so much gas in there under that high pressure that I'll have 81.654 atmospheres. I'm only going to drop it by 1.65 atmospheres. It's still going to have 80 atmospheres of pressure in there. And that balloon's going to be completely filled up. So I can probably fill that up close to almost 80 times. You know, it still fill that many balloons up if there's enough oxygen. Is that clear, or?
Yes.
But the answer is, okay, I'm going to do it, okay? I'm going to do the whole thing so you can see it. So here's what we got real quick. This is the gas container. Here's the balloon. Okay, so we're going to fill that balloon up with the gas that's in here. Okay, now I'm going to do it again. This is the last time. Pay attention. So what I need to know is, well, how many moles of gas do I need? I know the volume. I know the pressure. I know the temperature. I know the gas constant. The only thing I don't know about filling this balloon up is N, the number of moles. And N is PV over RT. Pressure, 1.05 atmospheres. Volume, 78.6 liters. 0.82 liter atmosphere, mole Kelvin. And temperature, 301 Kelvin. If I do that, the number of moles is equal to 3.343. So, that should make perfect sense. That's easy. We got a balloon, certain volume, certain temperature, certain pressure. I know exactly the number of moles that have to be in that balloon. Now, where am I going to get those moles? I'm going to get them from here. Now, we've already calculated this, and I know that now, right now, there are 165.412 moles of O2 inside here, right now. Now, how did I know that? Because I know the pressure, I know the temperature, I know the volume, because this is 50 liters. So I know there's that many moles in there. Does that make sense? Now, I'm going to subtract 3.343 moles. That's going to give me 162.068 moles of gas remaining of O2 in the tank. In the tank. That's how many is going to be left in there. Does that make sense? So now all I want to know, what is the pressure going to read when you have that many moles? So pressure is PV equals nRT over V. So 162.068 moles times 0.082, I'm leaving the units off right now, 301 Kelvin, divided by the volume is 50 liters. If I do that math, the pressure becomes 80.00 atmospheres. So, the pressure started at 81.654. If I want to fill that balloon up to 78.6, just let the gas out until the pressure drops down to exactly 80.00. Stop it, turn it off. You put exactly enough moles of gas in that balloon to fill it up to 78.6 liters. Am I clear? Okay, it's not that complicated. Light bulb's got to start going off on it. It just kind of makes sense, yeah.
So how'd you get the 165.412?
I got it from here because what do I know? I know the pressure, I know the volume, I know the temperature, right? So N equals PV over RT. So pressure, the volume, the temperature, and the rate constant. I know all four of those inside that container. So if you know the pressure, the volume, and the rate constant and temperature, all that's left is
You
number
just did
one.
the same exact thing you did before, but just for the tank.
Yeah, I started off, I want to know, well, how many moles of gas are in that tank? You know, and I easily calculated that by using N equals PV over RT. So now I know in that tank, there's this many moles of gas. Now, what if I calculated the moles of gas needed for the balloon and it was more than it was in the tank. Well, then I could never fill that balloon up all the way. But obviously, we only needed 3.3 moles. We had plenty. There's 165 of them. When we took 3.3 out, that's what's going to be left in the tank. And obviously, I can tell you what the pressure is going to be because you've reduced the number of moles. Make sense? Okay. So those are changing conditions, different types of things that we're looking at. So make sure you can do those types of problems. Okay. And we're going to do some stoichiometry with the gases. I think, did we do one of these already? No, we haven't. Did we do this one last time? Good, let's do this. Let's do it different. I'm going to do this one. I'm going to work this one out, then I'm going to give you guys one. This is the kind of stuff that we got to be doing here. Look at this equation. This equation says potassium chlorate, KClO3. You use your hands on some. This works very well. It will decompose. You've got to heat it up a little. You heat it up a little, the potassium chlorate will decompose into potassium chloride, and oxygen gas is released. So if you needed some oxygen gas, it'd be a good idea to have some of this around. You can produce your own oxygen gas. Now, calculate the volume of oxygen gas formed in the decomposition of 2.21 grams of potassium chlorate at STP. Okay, so we're going to calculate the volume of gas. Now, how do you calculate, if you want to calculate a volume, what's some stuff you need to know? You need to know the color of a gas? No, what do you need to know? Pressure is good. Pressure would be good. Number of moles would be good. Temperature would be good. If it's a gas, you got to have all those things. Well, we've got the temperature and the pressure, 1 atmosphere and 0 degrees Celsius, or 273, that's STP. So, if I got the pressure and the temperature, to calculate the volume, all I need is the number of moles. Because I have everything except the number of moles, since we want to calculate volume. So, we can get the moles from the stoichiometry. So let's do this. Now, you can see this in your notes. So, hopefully somebody's already looked up the molar mass of KClO3. Let me try something. Okay, so here we go. So we want the volume that is produced from this reaction. Well, the reaction tells me that 1 mole of potassium chlorate produces 3 moles of oxygen. There's the stoichiometry. Well, how many moles of potassium chlorate am I using? Well, 2.21 grams of KClO3. What's the molar mass? 122.5 grams per mole. So that equals, I'm going to do it slowly, 2.21 divided by 122.5, 0.1018 moles of KClO3. So, all I did was say, well, they gave me 2.21 grams of KClO3, I'm going to convert that to moles of KClO3. Because these numbers represent moles, not grams. Yes, sir?
Should that be a 2 or
Oh, should what be a 2?
like a 2 KCl?
It's 2 KCl.
Oh, it's 2 here. What about there? Oh, it is 2 then. Okay, that's good. Yes, we do need that. Okay, so 2 KClO3s gives 2 KCls plus 3 O2s. Okay, good. This doesn't change. So we still have 0.018 moles of KClO3, so we started with 2.21 grams. Now the stoichiometry. I see that 2 moles of KClO3 produce 3 moles of oxygen. So this math becomes times 3 and divided by 2 is 0.027 moles of O2. So, by starting with 2.21 grams of potassium chlorate, I easily was able to calculate the number of moles of oxygen that would form. Now, if I want to know the volume that oxygen would occupy, I'll use the ideal gas law equation. Volume is equal to nRT divided by pressure. N, 0.027 moles, times R, 0.082. I'm leaving the units off, but you should always put them on there when you're working. Temperature is 273 Kelvin, and the pressure is 1.0 atmosphere. Say again? we're at a standard temperature pressure 0 degrees Celsius. For gases, yeah, you're not freezing the gas. You're freezing water, you're not freezing the gas. Okay. So do all this math. 0.027 times 0.082 times 273 divided by 1 equals 0.604 liters. So that would be the volume, 0.6 liters. A little more than half a liter of gas, oxygen will be produced. Oh! Now think about this for a second. I just thought of a great way of saving Lindsay again. Instead of having oxygen, what if I said now, let's do it. Calculate the number of grams of potassium chlorate, KClO3, do I need to burn or decompose to produce enough oxygen to fill Lindsay's lungs up? What is the capacity of Lindsay's lungs? And we'll do it at STP, standard temperature and pressure. We'll say same temperature and pressure we are here. So go backwards. This is a great question. Now, I got to go to the store to get some KClO3. Exactly how many grams do I need to burn or decompose so I can produce enough oxygen to basically fill up 3-liter containers at standard temperature and pressure? So obviously you're starting here, not at 0.604. That number needs to be 3. You need to go backwards to figure out what the number of moles is to make it 3. Then you're going to work backwards to get the grams of KClO3. That's all you're going to do. Make it happen. My God. Raise your hand if you got an answer. I'm not going to pick on you. I just want to see if people are getting answers. And raise your hand if you're going to get an answer. You're just working on it. Raise your hand if you're not going to get an answer at all. Really? I can do this. These are the kind of questions I'm going to be asked. I like these kind of questions. What's the answer, Daniel? Who's got an answer? What's yours? Let me get you. Yeah, you, man. 10.94. 10.948 grams. And anybody concur with that number? I haven't done it. Okay, that looks like that's probably got to be the right answer. 10.94. Now I'm going to work it. Let me show you how she got it. What do I need? Pay attention closely. Let this make sense to you. I need to make 3 liters of 3 liters of oxygen gas. I need 3.0 liters of O2. You agree? That is a volume. And a volume is equal to nRT over P. If I want to know temperature is constant, pressure is constant, R is constant, the only thing that's going to be different is the number of moles. So I need to know, well, what number of moles is going to give me 3-liter volume? Well, let's rearrange this. N is equal to PV over RT. So this will be the number of moles that's going to give me 3 liters of gas or volume at standard temperature and pressure. Pressure, 1.0 atmosphere. Volume, 3.0 liters. R, 0.082. Temperature, 273 Kelvin. Is everybody clear with that? That's the pressure, the volume, the R constant, and the temperature. So 3 divided by 0.082 divided by 273 equals 0.134 moles of O2. Now, what do I know? This should make sense. I know. You can do this math all day long if you want to. If you have exactly 0.134 moles of O2, and you're holding that at standard temperatures and pressure, 1 atmosphere of pressure, 273 Kelvin, the volume of that gas is going to be exactly 3 liters. Exactly 3 liters. Does that make sense? It has to be. So I know that for a fact, this is the number of moles I need. Well, let's use our stoichiometry. 0.134 moles of O2. I see from the balanced equation that 3 moles of O2, so it'll cancel out, needs 2 moles of KClO3. That is true statement. Moles of O2 are going to cancel out. Now it's going to give me moles of KClO3, and I know that 1 mole of KClO3 is 122.5 grams of KClO3. So moles cancel out. So 0.134 times 2 times 122.5 divided by 3 times 1 is 3, and I'm imagining that's how you got your answer. 10 point, what was it? That's what it is. 10.93 grams of KClO3. So 10.93 grams of KClO3 would produce exactly 3 liters of oxygen at standard temperature and pressure. Is that clear?
Yes.
Those are all good questions. I like it. I'll probably put all those on the table. All right. Yes, ma'am.
So instead of that way, could you do the three?
Allison? Is this your name? Oh, what's your last name? Oh. Okay, I thought you were somebody else. Go ahead. What's your
Okay,
name?
so.
What's your name?
Oh, sorry, Liz.
Liz. Hello. I'm trying to get you.
So instead of doing that, could you take those 3.2 liters divided by the, what was it, 0.604 and multiply it by grams instead?
Oh, I'm sure you can. I'm not saying there's not a way, but I'm not going to give you shortcuts. I don't, because it's a relationship. I'm sure there's a ratio in there that you can set up for all kinds of things, but I'm not going to say, yeah, that's the one way. I'd have to sit there and look at it, but I'm sure you can. It's definitely a direct relationship to the number of, yeah, but I'm not gonna say yes or no. I want to see the stoichiometry work out, because I know you're not going to make a mistake there. Okay, all right. Let's try another one. Do this. This one, believe it or not, is a little easier, but you should be able to do this. Come on, work. Liz, in a way, this question's more in line to what you were thinking about. This one will work with what you're doing. That's how I would probably do it. Well, it says, it doesn't say, but it says at the same temperature and pressure. So you can use any pressure and temperature you want, as long as you stay the same on both sides. So use STP if you want. Raise your hand when you got an answer here. 1, 2, 2. You can do this, people. I know you can. 3. Oh, you ready? I mean, and you got the question in your notes, but look at this previous slide. Let that look at it. It should make sense to you. Remember Avogadro's law, 1 mole of any gas is the same exact volume as any other gas at the same temperature and pressure. You can use that relationship. We even did this one, standard temperature and pressure. We talked about this one last time. What's the answer? Just scream it out loud, everybody. Say it. 2.82 is correct. Now let me show you how easy this one was. So here's the equation. There's the equation that we're going to use. 3H2 plus N2 gives 2 NH3. Now, before I show you my work that's hidden under that pencil, let's look at what that's. Now, all these are gases, by the way. I don't have it up there, but they're all gases. Now, at standard temperature and pressure, what is the volume of nitrogen? You should know this. What is it? Why do you say 22.4? Because that is what it is. But well, how do you know? Because, well, you know that nitrogen up there is saying 1 mole of nitrogen. And you know that 1 mole of any gas at standard temperature pressure is 22.4 liters. Is that clear? Now, what is the volume of the hydrogen gas? Multiply that by 3. 3 times 22.4. Are you with me? Right? Now that's assuming we're at standard temperature and pressure. Now, you can adjust the pressure and the temperature to anything you want, and it doesn't matter. You're going to get the same answer. Exactly the same answer. So here, let's say I had 3 liters of hydrogen gas. If I had 3 liters of hydrogen gas, how many liters of nitrogen gas would I need to complete this reaction 100%? 1. 3 liters of hydrogen, 1 liter of nitrogen would make 2 liters of NH3. Is that clear? You can adjust the pressure to make that happen. So that relationship I can use simply. If I have 4.23 liters of hydrogen, I can see from here that 3 liters of hydrogen would make 2 liters of NH3. That's a true statement. No matter what the temperature, you can adjust it as long as you keep it the same. So therefore, you get 2.82 liters of NH3. Now, I can do this a longer way to prove to you that no matter what number you come up with, if I said, Johnny, cash, pick the pressure. Any pressure will do. 20 atmospheres. We're going to do this. This is good work. 20 atmospheres. Okay, so pick a temperature. Wow, he did a good one. 583 Kelvin. I'm going to use these temperatures and this pressure and do this calculation again the long way without using that relationship and show you that I'm going to get exactly the same number. Because I need you to see this. I need you to work this out for yourself to start getting these relationships and letting them make sense to you. So, we started with 4.23 liters of hydrogen gas. So I want to first convert that to moles of hydrogen. So moles, N is PV over RT. Pressure, 20 atmospheres. Volume, 4.23 liters. R, 0.082. Temperature, 583 Kelvin. Quickly, do that math. 20 times 4.23 divided by 0.082 divided by 583 equals 1.77 moles of H2. Okay, so I have 1.7 moles of H2. Are you with me? He picked those numbers. I didn't pick them. Now I'm going to use the stoichiometry. It says that 3 moles of H2 will make 2 moles of NH3. So now I can get the number of moles of NH3 that was formed. So times 2 divided by 3 is 1.18 moles of NH3. I use the stoichiometry. Now I'm going to go backwards and calculate the volume that NH3 would be, because volume is nRT over P. The number of moles, 1.18. The R, 0.082. The temperature of 583 Kelvin. Divided by the temperature, 20 atmospheres. 1.18 times 0.082 times 583 divided by 20 equals 2.82 liters. Exactly the same number. So it doesn't matter, the relationship is in there. So does this kind of make sense to you? A little bit. I need it to. These are good relationships. Yes, ma'am.
So whatever temperature and pressure you plug in there, you're going to come out.
You'll get the same, so you'll get the 2.82 liters no matter what you use for pressure and temperature. Because the relationship is what we're working on here. The relationship says that 3 amounts of hydrogen is going to make 2 amounts of ammonia. So if you have 4.23 liters of hydrogen, I know that 2/3 of that will be the amount of ammonia, no matter what. Now, by using the pressure and the temperature that we came up with a number of moles, use the stoichiometry, put the moles back in to get a volume, and we're going to get exactly the same answer because the relationship is always always going to hold because chemistry is an exact science. It's going to happen exactly every time if you hold all the variables the same. Yes, sir.
Does that happen because R, P, and T are in different, is this just a numerator and denominator?
Yes, they're constant. They remain the same. So essentially they cancel themselves out every time on both sides. For the beginning and then the end, they're going to cancel each other out, so it doesn't matter. That's exactly right. Okay, I got to move on from that. Now, that's stoichiometry using the gas laws, and I want you to really look at some homework problems like that, because I like